Welcome back to analog electronics, and this is lecture number 30. And in the last two classes, actually last many classes, what we did was we worked over the common source, common gate, common drain amplifiers with capacitance. Then we looked at the cascode amplifier and as well as the cascaded amplifier with the presence of capacitance. We worked out all of these over the last several classes. Then at the end of the last class, we also discussed Miller's theorem approximation, right, and we figured out that when you have a floating capacitor, how to deal with it, right. That might not be the right way all the time. In fact, this Miller's theorem works only under some circumstances in some very specific places. So, do not just use it here and there. Okay. It is generally you avoid it until I tell you that this is one place where Miller's theorem is going to give you a reasonable answer. Okay. Only then use it over there. All right. Now, today what we are going to do is we are going to take a slight diversion. Now, the diversion that we are going to take is related to Bode plots. So, earlier you had seen Bode plots, right. When there are two poles, at each pole there is going to be a 20 dB per decade negative slope extra. Right, this is your Bode plot. So, if my pole is over here, so suppose this is 40 20 0 dB, then over a decade you are going to get a drop of 20 dB per decade, right. That is the idea after the pole. And suppose you have a second pole somewhere over here, okay. Then now over a decade, so this is a decade, you are going to get a slope of, you are going to get minus 40 dB per decade, right. So, minus 40 dB decrease. Something like this, fine. I am taking advantage of the boxed paper that I have, grid lines are there. Anyway, this is how the Bode plot is going to be. And similarly, you are going to have a phase plot. So, for the phase plot at the pole, you are going to get minus 90 degrees. At every pole, you are going to get minus 90 degrees. Something like this. All right, this is going to be your Bode plot of a two pole system. Now, why we are going to do the two pole system is because we saw that in the cascode amplifier as well as the cascaded amplifier, right. Whenever there are two stages, you are going to see that you are going to get a two pole system, and both in case of the cascode as well as the cascade, the denominator was did not give any closed form pole locations. Actually, you could have done it, you could have factorized using Sridharacharya, but it is going to be such a gigantic expression that it is not worth writing. Okay. So, that is why we are looking at two pole systems today. All right. Now, there are two important things. One is when you are making an op amp, why are we doing all of this? Why are we studying this course? Most of it is towards trying to build an op amp. Okay. So, when we are trying to build an op amp, we always must have an understanding that tomorrow, after we have finished making this op amp, tomorrow we are going to use this op amp. How? In the presence of feedback. Okay. So, the op amp is always going to be used in the presence of feedback. All right, this understanding has to be there. Remember, like we discussed, you need DC negative feedback for the operating point to be set, correct. So, feedback is absolutely required, you are never going to use the op amp without feedback. Okay. In fact, in very special situations where you start using an op amp without feedback, in such situations the op amp is not even called an op amp, it is called a comparator. All right. So, we stop calling it an op amp when we do not have feedback. So, as long as it is an op amp, we have to understand that in future, after we have finished making the op amp, we are going to use it in the presence of negative feedback. Okay. Now, there are some very important tools in control theory that analyze systems that are going to be used in negative feedback. Remember, the op amp itself might have poles in the left half plane. Okay. All the poles of the op amp might be in the left half plane, but when you use it in negative feedback tomorrow, are the poles still in the left half plane? The poles of the overall system, complete system, right. The system is going to be some forward loop H in the presence of feedback H divided by 1 plus H, something, or H times G, some complicated stuff. Now, are the poles of that system in the left half plane? Can you guarantee? Okay. Now, in control theory, there are some excellent tools that can predict that when I use this system in feedback later on, are the poles going to still remain in the left half plane, or will something jump to the right half plane. Okay. So, you probably know the names of Routh-Hurwitz criteria, Nyquist criteria, right, and then there was something called related to Bode plot, right. Then you would have studied, so first you would have studied Routh-Hurwitz, then you would have studied Nyquist criteria, then would have come the time to study Bode plots, and at the end of studying Bode plots, they would have talked about gain and phase margin. Okay. So, in circuits we normally like gain and phase margin a lot, right. I mean, you draw this Bode plot, and then you can tell by looking at the plot. Okay, first of all, by looking at this plot, offhand you know that P1 and P2 are in the left half plane. If P1 and P2 are in the right half plane, then sorry, okay, nothing works. If a pole happens to go to the right half plane straight away, then do not bother, right, that is no good. Now, the assumption is that P1 and P2 are already in the left half plane. Okay. Now, that they are in the left half plane, the op amp by itself is going to be stable. Why 2 poles? It can have 5 poles, right. As long as the poles are in the left half plane, the op amp is stable. But tomorrow when I use the op amp in a negative feedback system, is that system going to be stable or not? That is the question that we want to ask. Okay. And the answer to that is that we can examine the gain or phase margin. Gain and phase margin both tell the same story, exactly the same story, right, and they are reported from exactly the same plot, right. You can from the same plot you can estimate gain margin as well as phase margin. Sometimes it is easier to estimate the gain margin, sometimes it is easier to estimate the phase margin. Okay. But both of them say exactly the same story. So, the story is that if gain margin is not there, then the system is going, gain margin or phase margin is not there, then the system is not going to be stable when you place it in unity gain negative feedback tomorrow. Unity gain negative feedback is the worst possible negative feedback. Okay. Unity gain means the feedback factor is 1. Okay. H is the forward path, feedback path is G, G is equal to 1, that is the worst case. Okay. That is when the most problems happen in control theory, and under such scenarios is the system stable or not, right. Normally you are never going to have feedback gain, that feedback path should always be some less than 1, not more than 1. Okay. So, the largest number you are going to have over there is 1. Why? Why do I say such a thing? Because this is what I am talking about. Okay. So, this G is what I am worried about. H is my op amp. H has super high gain. H has gain which is close to infinity. All right. Now, if I want this whole thing to work as an amplifier, then how does it work? If this is an input V, then the error has to be 0 because H has gain of infinity. That means what has been fed back is also V, which means that the output of H is V divided by G, okay, because that is what is coming into G. So, H is very large, H is infinity. The output has nothing to do with H, it has everything to do with G. All right. So, normally we want this feedback factor to be a factor less than 1, right. A lot of people call it beta, right. This is called A and this is called beta, right. The feedback factor is beta. This feedback factor is to be kept less than 1 because otherwise you are not amplifying. If G is not less than 1, then the output is going to be smaller than the input, which seems like a flop. Okay. So, you certainly want G to be something smaller than 1, right, and therefore, the worst case G is 1. All right. The largest possible value of G is 1. All right. So, when the feedback factor is 1, is this system stable or not? Is this open loop system? This is the open loop system. Tomorrow I am going to place this open loop system in closed loop system with a feedback factor of 1. At that time, is it going to be stable or not? Right? I am trying to clarify. Right? This is a common misconception, very common misconception. If you read the book, you are not going to be sure of what is going on. Right? Is the op amp not stable? No, the op amp is stable. But when I place this op amp tomorrow in a negative feedback, unity gain negative feedback system, is that system going to be stable or not? That is the question that we are trying to answer. And the way we do that is by examining the gain margin or the phase margin. So, gain margin is defined as the excess gain below 1 when angle H reaches, when the phase reaches minus 180 degrees. Excess gain below 1 means if it is 1 by 5, then the gain margin is 5. Okay. If magnitude of H is 1 by 5 when angle of H reaches minus 180 degrees, then the gain margin is a factor of 5. If magnitude of H is 0.01 when angle of H reaches minus 180 degrees, then the gain margin is a factor of 100. Okay. So, that is what I mean by excess gain below 1. How much is the gain less than 1 when angle H reaches minus 180 degrees. This is one question, this is gain margin. And the alternate one is phase margin, and phase margin is defined as what is the phase, how much is the phase more than minus 180 degrees when magnitude gain reaches 1. One means 0 dB, just by the way, reminder. Okay. So, what does this mean? At the point when magnitude of H reaches 0 dB, I check my phase, is that phase more than minus 180 degrees? If it is more, how much more? If it is minus 135 degrees, then the phase margin is 45 degrees. If it is minus 120 degrees, then the phase margin is 60 degrees. If it is minus 200 degrees, then the phase margin is negative 20 degrees. Okay. So, in either case, when the gain margin is negative in dB or when phase margin is negative in degrees, then the system is going to be unstable when placed in unity gain negative feedback. However, if both of these are, if either of these, if one is positive, the other will also be positive. If you have got positive gain margin, positive phase margin, then the system is going to be stable when you place it in unity gain negative feedback. All right. So, this is the theory, this is coming from your control engineering. All right. We are not going to try to prove it, that is not our business over here. I am just going to state this. All right. Now, let me look at my particular plot over here. I have had two poles P1 and P2, and if you try to look at what is the gain margin or the phase margin, let us try to look at what is the phase margin for example. So, when the at the frequency when the gain reaches 1, that is 0 dB, at that frequency my phase is minus 180 degrees, okay, or it is asymptotically reaching minus 180 degrees. So, either there is no phase margin or slight amount of phase margin, something of that order, right, 0 or close to 0 degrees of phase margin. So, it might be in fact hard to measure. All right. If there was a third pole, we would have been sure, because it would not asymptotically reach minus 180 degrees. If there was a third pole, then it would again go and we would know that it is reaching minus 180 degrees. All right. So, in any case, this particular system, the phase margin is very little. If this is your op amp Bode plot, people are not going to be very happy with this op amp, because they will say that with temperature or with operating conditions, if my Bode plot changes slightly, then my system is going to become unstable, and instability is something that people are not ready to tolerate. So, the customer is not going to purchase your op amp. Fine, if this is the Bode plot of your op amp, no customer is going to be eager to purchase your op amp. All right. So, the question is where should P1 and P2 be such that my customers are eager to purchase my op amp. All right. So, a rule of thumb is that a good design is going to have a phase margin of 60 degrees, right. This is some general guideline. This is general guideline that 60 degrees of phase margin is considered nice by most customers. Some customers are okay with even lesser phase margin, right. Some very aggressive customers will say that all right, 45 degrees will not be a bad idea, right. Somebody who is trying to make a very cheap cell phone, right. He does not care if his customer is unhappy, right. You get what you pay for, right. So, he is going to sell his cell phone dirt cheap. So, maybe he is going to cut a lot of corners. So, this is a corner that he is going to cut. He is going to say that all right, 60 degrees is too safe, right. Give me an op amp with phase margin of 45 degrees. He is very aggressive, right. Then again there are going to be customers, let us say you are in the your customer is the military, and these military guys will say no, 60 degrees is too aggressive, let us play it safe, right. Our missile should not suddenly point at us and start shooting at us, okay. It should not go out of control. We need everything guaranteed to be stable. Give me 90 degrees of phase margin. All right. So, this phase margin number depends on what kind of customer you have. An aggressive customer will ask for 45 degrees, a very strict customer is going to ask for 90 degrees of phase margin, right, like the military. 60 degrees of phase margin is a nice clean number, right. It is safe, it is considered safe as a you get best of both sides. All right. So, let us evaluate our system. Okay. So, our system is h of j omega all right, and let us say or h of s, whatever you want to call it, and let us say it has a DC gain of A naught, and it has two poles. On the negative real axis, okay, two poles on the negative real axis, one at minus omega 1 and the other at minus omega 2. Fine. So, what do we have to do over here? We have to find out magnitude h of j omega, right. Then we have to find out what is omega at which magnitude h of j omega reaches 1, that is 0 dB. Let us call that frequency omega naught. Right. First you have to answer this question, then you have to plug in that omega naught into h of j omega naught and find the phase. Right. And you have to make sure that that phase is some, let us say that the target phase margin is an angle phi. Okay. So, you have to make sure that that phase is phi degrees above minus 180 degrees. All right. So, this is the plan. We need to do this. Fine. Okay. So, if I want h of j omega to be phi plus minus pi, what do I engineer? I have to engineer the locations of omega 1 and omega 2 such that this happens. All right. So, what is the constraint on? All right. So, this is what we are going to try to do right now. So, first we are going to find out, we are going to answer this question, at what omega equal to omega naught is modulo h of j omega equal to 1. Then we are going to find the phase, then we are going to say what is the constraint on omega 1 omega 2 such that the phase is equal to phi minus pi. All right. So, this is how I am trying to set up the problem. So, first of all, modulo h of j omega is equal to 1 and h of j omega is a naught okay. I made a mistake? No. Modulo is what? Okay. And what is angle? What is the angle? Minus tan inverse omega by omega 1 minus tan inverse omega by omega 2. Okay. Each of these contributes a phase, right. The phase of the first one, real part is 1, imaginary part is omega by omega 1. Therefore, the phase of this is tan inverse of omega by omega 1 divided by 1, alright, but this is in the denominator. So, a minus sign comes. So, the overall phase from this particular component is minus tan inverse omega by omega 1. Component of this is minus tan inverse omega by omega 2. Alright, this is understood. We are doing same trigonometry. Alright. So, this is the basic stuff. Now, we are going to say that at h of j omega naught modulo is equal to 1. Omega naught is such that modulo h of j omega naught is equal to 1, which means that if I plug in omega naught over here, then 1 plus omega naught squared by omega 1 squared times 1 plus omega naught squared by omega 2 squared is equal to a naught squared. Okay, this is one thing that we know. Okay, so, omega naught you can, this is a quadratic in omega naught squared, right, you will get omega naught power 4, right, you can multiply and then you can solve a quadratic, you can waste a lot of time, right, you can do that and then you can plug in that omega naught, the value that you got from that quadratic into this tan inverse, right, it is going to be quite horrible, right, let us not do that, alright, that is way too much. Okay. Now, instead what we are going to do is let us look at the phase over here, let us not try to solve for omega therefore, alright. So, initially I said that I am going to solve for omega, right, but after setting up this equation I am now suggesting that let us give up, let us not solve for omega, because trying to solve for omega is going to break your back, alright, we are not going to do that, we are all engineers, right, anything is too hard we are not going to do it. Instead let us look at this from the back side. Okay. What is angle h of j omega naught? So, angle h of j omega naught is so much. At omega naught, at omega equal to omega naught, it is equal to just plug in omega naught, so much, alright. And now I am going to do something very special, I am going to take cos of both sides of this expression. So, first of all I want angle h of j omega naught to be equal to what? I want it to be equal to phi minus pi. Alright, this is what I want it to be equal to. Now, let me take cos of both sides. So, what is cos of phi minus pi? So, let us say this is an angle phi 60 degrees, phi minus pi is 60 degrees minus 180 degrees. So, that is minus 120 degrees. Okay. So, what is cos of minus 120 degrees? It is going to be all sin tan cos, right, if you think of it. Yes, cos is base by hypotenuse, right. Here the base is negative, the hypotenuse still has a solid value, it is still positive. Therefore, it is going to be cos is going to be negative. So, this is going to be minus cos of phi. Okay. Cos of phi minus pi is nothing but minus cos of phi, and if I take cos of minus something, then that is the same as cos of the sum. Now, look, it has been a long time since I studied trigonometry. I have completely forgotten all my trigonometry. I remember very little. Okay. But I am going to try to do this in a way to help you out. I do not remember. Okay. I can't do cos of tan inverse A minus plus tan inverse B. That is expecting too much from me. Okay. I do not remember this. But let us try to understand that cos of something plus something is nothing but cos something minus sine of something right. Cos of A plus B is cos A cos B minus sin A sin B, that much I remember. Okay. So, if I want to evaluate this, then all I have to work out is what is cos A, what is cos B, what is sin A, what is sin B, where A and B are these tan inverse things. All right. Now, think of a situation. So, what does tan inverse omega naught by omega 1 mean? It means that you have got a triangle where the height is omega naught and this is omega 1, and this is the angle we are interested in. Okay. Now, what is going to be cos of the same angle? Cos of the same angle will be omega 1 by the hypotenuse. Okay. So, cos of the first one, so let us call this capital A, let us call this capital B. So, cos of A will be equal to omega 1 by square root of omega naught squared plus omega 1 squared. Am I right? I think I am right. And likewise, cos of B will be equal to omega 2 by square root of omega naught squared plus omega 1 squared, omega 2 squared. Okay, because B was omega naught by omega 2, right. And by the same argument, sin A is going to be omega naught by root over omega naught squared plus omega 1 squared, and sin B is omega naught by root over omega naught squared plus omega 2 squared. All right. So, I have just written down these expressions on the side, and then I am going to do cos of A plus B equal to cos A cos B sin A sin B, right, and therefore, I get minus cos phi is equal to omega 1 omega 2 by square root of omega naught squared plus omega 1 squared, omega naught squared plus omega 2 squared, minus sin A sin B, where sin A and sin B are Is this okay? And now the magic is going to happen. Look at this, omega 1 omega 2, let's divide the denominator by omega 1, this becomes a 1, I get omega 1 squared, this becomes a 1, I get omega 2 squared. Fine. And likewise, let us take omega 1 omega 2 common over here, this becomes a 1, this divides by omega 1 squared, this becomes a 1, this divides by omega 2 squared. And then comes even more magic. Okay. From my previous relationship, I know that this product is actually equal to A naught squared. Is this okay? So, this is it. So, if I want the phase margin to be an angle phi, then minus cos phi has to be equal to 1 by A naught times 1 minus omega naught squared by omega 1 omega 2, or you could rewrite this as cos phi has to be equal to A cos phi, A naught cos phi has to be equal to okay. So, this is a key relationship, you can place this one on the other side. The product of omega 1 omega 2 have to be such that omega naught squared by omega 1 omega 2 has to be equal to 1 plus A naught cos phi, where omega naught is the unity gain bandwidth. Right, the frequency at which the gain was 1. So, it is called unity gain bandwidth. All right. So, at that frequency the gain is equal to 1, I call it unity gain bandwidth magnitude, h of j omega was equal to 1, that was my definition of omega naught. Fine, my two poles have to be arranged in this fashion. If I do not, then I will not get a phase margin of phi. If I want a phase margin of phi, then 1 plus A naught cos phi has to be equal to so much. Or in other words, let us try out some numbers. Let us say phi is 60 degrees. Okay. What is cos phi? Cos phi is root 3 by 2. 1 by. So, this is 60 degrees. I am sorry, I am really bad at trigonometry. Base, yeah, cos 60 degrees is 1 by 2. Yeah. So, 1 plus A naught by 2 has to be equal to omega naught squared by omega 1 omega 2. Okay. So, this is a relationship that we have to follow. And where has this come from? From nothing, from some transfer function, okay, from a random. I mean I have assumed nothing, no assumptions have been made, right. All that I have said is that this transfer function has two poles. I have worked out, I could not quite get to this point, what is the value of omega naught, I kind of gave up, all right. But then I tried to link the two of them together and I came up with a constraint on omega 1 and omega 2, all right. So, this is what we have done so far, and what we are going to do is we are going to take this forward in the next class. We are going to see what this means in terms of our transfer functions, right, the transfer functions that we have, what does it mean in terms of that. Okay. So, let us stop here and we are going to carry on with this in the next class. Thank you.